Imagine standing in a place where time itself was just learning to tick, where the very concepts of space and matter were being written for the first time in the cosmic book of existence. Not the emptiness we think of as the void between stars, but a place so dense, so impossibly hot, that every law of physics we know would dissolve like morning mist. This was the beginning of everything, not just our Earth, not just our solar system, but every atom, every photon, every gentle breath you're taking right now as you settle in to listen. Hello and welcome to the Sleepy Astronomer. Tonight we're drifting back through time itself, all the way to the very first moment when the universe began its long, patient journey toward becoming the cosmos we know today. A journey that started 13.8 billion years ago in conditions so extreme they almost defy imagination, and led, through countless small steps and cosmic coincidences, to this quiet evening where you can rest comfortably and contemplate the grandest story ever told. Whether you're tucked into bed, curled up on a favourite chair, or perhaps lying back where you can see the night sky through a window, I'm so glad you're here. If you're settling in for the first time, welcome aboard our gentle journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Our journey begins not with telescopes or equations, but with something far older and more universal, the human need to understand where we came from. Every culture that has ever looked up at the night sky has wondered about beginnings. Some spoke of cosmic eggs hatching in the darkness, others of words spoken into the void that brought forth light and matter. These ancient stories, beautiful in their own right, were humanity's first attempts to grasp something almost ungraspable. How something came from nothing, how the infinite complexity around us emerged from simplicity. Tonight, we'll explore how modern science has given us what might be called a new creation story, one written not in poetry and metaphor, but in the language of physics and observation. The Big Bang Theory isn't just an abstract idea, it's a detailed account of the universe's first moments, supported by evidence we can see and measure today. Yet like the ancient myths it echoes, it speaks to something profound about our place in the cosmic story. We'll drift gently through the evidence that led scientists to this remarkable conclusion, the expanding universe that Edwin Hubble revealed, the ancient light still glowing faintly in every direction we look, the precise ratios of elements forged in the cosmic fire of those early moments. We'll explore the timeline of creation itself, from the first inconceivable fraction of a second when the laws of physics were still taking shape, through the cooling and expansion that led to the first atoms, the first stars, and eventually to worlds like ours. There's something deeply comforting about understanding our cosmic ancestry. Every carbon atom in your body was forged in the heart of a star that lived and died long before our sun was born. Every breath you take contains nitrogen created in the nuclear furnaces of stellar cores. The calcium in your bones, the iron in your blood, the oxygen that keeps you alive, all of it has a story that stretches back to the very beginning of time. But this isn't meant to be a technical lecture. Instead, think of tonight as a gentle meditation on the most extraordinary journey ever taken, the universe's path from a single, infinitely small point to the vast, star-filled cosmos that cradles us tonight. We'll move slowly through these concepts, pausing to appreciate not just the science, but the wonder of it all. So, find your most comfortable position, whether you're nestled under soft blankets, resting in your favourite chair, or perhaps lying where you can glimpse the stars through a window. Take a deep breath, and let's begin our gentle drift backward through time. Past yesterday and last year, beyond the formation of our solar system, further back than the birth of the first stars, all the way to that first moment when time itself began its slow, steady march toward this peaceful evening. Out there, in that first instant of creation, the entire story of everything was just beginning to unfold. Patient, mysterious, and beautiful, ready to reveal how we came to be part of this infinite, expanding tapestry of space and time. Long before humans built telescopes or wrote equations, we told stories about beginnings. Not the kinds of stories you'd find in textbooks, but deeper, more primal tales, whispered around fires under star-filled skies. Stories of cosmic eggs cracking open in the darkness, of words spoken into the void that brought forth light, of sleeping giants whose dreams became the mountains and seas. These weren't primitive attempts at science, they were something more profound. They were humanity's first recognition that the universe had a story, and that we were somehow part of that story. In ancient Egypt, priests would gather in the pre-dawn darkness of temples dedicated to Ra, watching for the first hint of sunrise over the Nile. To them, each dawn wasn't simply the return of daylight, but a daily reenactment of creation itself. They believed that before anything existed, there was only Nun, an infinite ocean of dark, motionless water. From this primordial sea arose Atom, the first god, who spoke light into being and began the long process of separating order from chaos. Every morning, Ra's journey across the sky repeated this cosmic victory, reminding anyone who watched that creation wasn't a single event, but an ongoing process of bringing light and structure to an otherwise formless universe. Halfway around the world, in the frozen landscapes of Scandinavia, the Norse told a different story, but one that touched on remarkably similar themes. Before there were stars or planets, they said, there was only Ginnungagap, a yawning void surrounded by realms of ice and fire. When the cold and heat finally met in that emptiness, the collision created not just matter, but time itself. The first being to emerge was Ymir, a giant whose body would eventually become the raw material for everything we see around us. His flesh became the earth, his blood the seas, his bones the mountains, and his skull the dome of the sky. It's a story that speaks to something we still grapple with in modern cosmology, the idea that the universe's structure emerged from the interplay of opposing forces in what was once an empty void. These ancient stories shared something remarkable, whether they came from the deserts of Egypt, the fjords of Norway, or the river valleys of Mesopotamia. They almost all began with emptiness, a void, an abyss, a great silence waiting to be broken. And then, through some cosmic trigger, a word, a thought, a collision, that emptiness gave birth to everything. It's almost as if our ancestors intuited something about the nature of creation that would take modern science thousands of years to rediscover. But perhaps the most intriguing aspect of these creation myths is how they handled the question of time itself. Many cultures, particularly in India and parts of the Americas, imagine time not as a straight line with a clear beginning and end, but as great cycles, vast cosmic wheels turning slowly through periods of creation, preservation, and dissolution, only to begin again. In Hindu cosmology, the universe breathes in cycles called kalpas, each lasting billions of years. During each cycle, entire universes are born, mature, age, and eventually dissolve back into the primordial ocean of possibility, only to emerge again in the next cosmic dawn. It's a vision that resonates oddly with some modern theories about multiple universes and cosmic inflation. These weren't just stories, though. They were humanity's first attempts at what we might now call natural philosophy, careful observations of the world wrapped in narrative frameworks that could be remembered, shared, and passed down through generations. Ancient sky watchers noticed that the heavens seemed eternal and unchanging, the same constellations wheeled overhead year after year, century after century. The planets wandered their predictable paths among the fixed stars. The sun rose and set with mathematical precision. To minds trained to see purpose and pattern in everything, this cosmic clockwork suggested something profound about the nature of existence. The ancient Greeks took this observational approach and began to formalize it. Philosophers like Aristotle looked up at the night sky and saw what seemed like perfection. Celestial spheres carrying the sun, moon, and planets in eternal circular motions around a stationary Earth. To them, this wasn't just beautiful, it was philosophically necessary. The heavens, they reasoned, must be perfect and unchanging, because change implied imperfection, and the cosmic realm was surely the domain of the eternal and divine. This idea of an unchanging eternal universe would dominate Western thought for nearly 2,000 years. But even within this framework of cosmic permanence, questions about beginnings persisted. If the universe was eternal, how did it get started? Some Greek thinkers, like Democritus, proposed that everything was made of tiny invisible particles, atoms, moving randomly through infinite space, occasionally coming together to form the temporary structures we see around us, including ourselves. Others, following Plato and Aristotle, insisted that the universe was not only eternal but also purposeful, guided by some cosmic intelligence toward goals we could glimpse through careful observation and reasoning. The tension between these views, random chance versus purposeful design, temporal beginning versus eternal existence, would echo through philosophy and early science for centuries. When Islamic scholars in the medieval period began to study and extend Greek knowledge, they brought new perspectives shaped by their own cultural understanding of creation. Thinkers like Al-Ghazali grappled with the question of whether the universe had a definite beginning, as suggested by Islamic theology, or was eternal, as Aristotelian philosophy seemed to demand. Their debates weren't purely abstract. They were trying to reconcile careful observation of the natural world with deeper questions about meaning and purpose. European scholars in the medieval and Renaissance periods inherited these debates along with Greek and Islamic learning, but something began to shift in how they approached these questions. Instead of relying purely on philosophical reasoning, a few bold thinkers started to suggest that understanding the universe required more than just thinking about it. It required looking at it with fresh eyes, making careful measurements, and being willing to challenge even the most ancient and respected authorities. This shift reached a kind of crescendo with Nicholas Copernicus in the 16th century. Copernicus wasn't trying to revolutionize cosmology when he began his careful study of planetary motions. He was simply trying to make sense of the increasingly complex mathematical models needed to predict where the planets would appear in the sky. The traditional Earth-centered system required elaborate mechanisms, circles within circles, to account for the observed motions. But when Copernicus experimented with putting the sun at the center instead, the mathematics became elegantly simple. The planets, including Earth, were simply orbiting the sun in orderly paths. This wasn't just a technical improvement, it was a fundamental reimagining of our place in the cosmos. Earth was no longer the immovable center of everything, but one world among many, circling a star that was itself likely just one star among countless others. The implications rippled outward like waves from a stone dropped in still water. If Earth wasn't the center of the universe, if the heavens weren't perfect and unchanging, then what other assumptions about the nature of reality might need to be reconsidered? Galileo Galilei, peering through his small telescope in the early 1600s, began to see evidence that the heavens were indeed changeable. The moon had mountains and craters, like a world of rock and stone rather than a perfect celestial sphere. Jupiter had moons of its own, proving that not everything in the sky orbited Earth. The Milky Way resolved into countless individual stars, suggesting that the universe was far vaster than anyone had imagined. Each observation chipped away at the ancient certainty that the cosmos was small, Earth-centered, and unchanging. By the time Isaac Newton developed his laws of motion and gravity in the late 1600s, the stage was set for an entirely new kind of creation story. Newton's mathematics could explain the motions of planets and moons, the paths of comets, even the tides on Earth, all through the action of a single, invisible force, gravity, operating according to precise mathematical laws. But Newton's universe, while mechanically elegant, raised new questions about beginnings. If gravity pulled all matter together, why didn't the universe collapse under its own weight? Newton himself recognized this problem and suggested that perhaps the universe was infinite in extent, with matter distributed so evenly that gravitational forces balanced out on the larger scales. This idea of an infinite, eternal, mechanically perfect universe became the dominant scientific worldview for the next 2 centuries. It seemed to solve the ancient problem of cosmic beginnings by essentially declaring that there was no beginning. The universe had always existed in more or less its current form, governed by timeless mathematical laws. The great French mathematician Pierre-Simon Laplace famously claimed that if he knew the position and velocity of every particle in the universe, he could predict the entire future and retrodict the entire past. The universe was like a vast, complicated clock, ticking away according to predictable rules. But even as this mechanistic vision reached its zenith in the 18th and 19th centuries, new observations were beginning to raise uncomfortable questions. Astronomers were discovering that the universe was far stranger and more dynamic than Newton's clockwork cosmos suggested. They found stars that flickered and changed brightness, nebulae that seemed to spiral and shift over time, and most puzzling of all, a universal tendency for distant objects to appear redder than they should. The story of how these observations eventually led to our modern understanding of cosmic beginnings is itself a kind of creation myth, not born from ancient wisdom passed down through generations, but from the patient accumulation of evidence, the careful testing of ideas against reality, and the willingness to abandon even the most cherished beliefs when the evidence pointed in new directions. Albert Einstein, working in the early 1900s, created a new mathematical framework for understanding space, time, and gravity that was even more elegant than Newton's, but led to a startling conclusion. According to Einstein's equations, the universe couldn't be static and eternal as everyone had assumed. Space itself was either expanding or contracting, and if that was true, then tracing the expansion backward would lead to a moment when everything in the universe was compressed into a single, impossibly dense point. Einstein himself was so troubled by this implication that he modified his equations, adding what he called the cosmological constant, a kind of cosmic repulsion that could balance gravity and keep the universe stable and eternal. It seemed like a reasonable solution to an unreasonable problem. How could the entire universe have a beginning? What would that even mean? The answer came not from more mathematics, but from an American astronomer named Edwin Hubble, working with the largest telescope in the world at Mount Wilson Observatory in California. In the 1920s, Hubble made observations that would forever change our understanding of the cosmos. He found that distant galaxies, entire islands of billions of stars, were moving away from us. And not just moving, but moving in a very specific way. The more distant a galaxy was, the faster it appeared to be receding. This wasn't just motion through space. It was the expansion of space itself. The universe wasn't static at all, but growing larger with each passing moment, like a balloon being slowly inflated. And if the universe was expanding now, then in the past it must have been smaller, denser, hotter. Tracing this expansion backward led to an inescapable conclusion. There was a moment, roughly 13.8 billion years ago, when the entire observable universe was compressed into a volume smaller than a single atom. Georges Lemaitre, a Belgian physicist and Catholic priest, was one of the first to fully grasp the implications. He called it the primeval atom, a cosmic egg that somehow hatched into everything we see around us. The term Big Bang came later, coined somewhat dismissively by astronomer Fred Hoyle, who preferred to believe in a universe that created new matter continuously rather than one that began in a single explosive moment. But the evidence kept accumulating. In the 1960s, 2 radio astronomers accidentally detected a faint hiss of radiation coming from every direction in the sky, the afterglow of creation itself, still warming the universe nearly 14 billion years after that first moment. Other observations confirmed that the lightest elements in the universe, hydrogen and helium, existed in exactly the proportions that would be produced in the nuclear furnace of the early universe. And so, through centuries of observation, debate, mathematical insight, and technological advancement, humanity arrived at a new creation story. Not one born from intuition and poetry, though it has its own deep poetry, but one built from evidence we can see and measure. The Big Bang theory suggests that everything we know, space, time, matter, energy, the laws of physics themselves, emerged from a single, unimaginably hot and dense state and has been expanding and cooling ever since. Yet in many ways, this scientific creation story echoes the ancient myths our ancestors told around their fires. Like those old tales, it begins with emptiness, not the void of space, but the absence of space itself. Like them, it describes a moment when opposing forces came together to create structure from chaos. And like them, it suggests that we are intimately connected to cosmic beginnings, not just observers of the universe, but participants in its ongoing story. The ancient Egyptians saw creation reenacted every dawn. We now know that the light reaching our eyes from the most distant galaxies has been travelling toward us for billions of years, carrying information about the universe when it was young and hot and very different from what we see today. In a sense, every time we look up at the night sky, we're witnessing creation, not its daily repetition, but its actual unfolding across cosmic time. These creation stories, both ancient and modern, speak to something fundamental about human nature. We are creatures who need to understand our beginnings, to place ourselves within a larger story that gives meaning to our brief existence. Whether that story involves cosmic eggs or expanding space-time, sleeping giants or cooling plasma, the deep human need remains the same, to know where we came from, how we fit into the vast scheme of things, and what our place might be in the ongoing adventure of existence. When most people hear the words Big Bang, their minds often conjure up an image of a tremendous explosion somewhere out in empty space, perhaps a cosmic bomb going off in the darkness, hurling matter and energy outward like shrapnel from some unimaginable detonation. It's a natural image to form, given the name, but it's not quite right. The Big Bang wasn't an explosion in space at all. It was something far stranger and more profound. It was the birth of space itself. Imagine, if you can, the absence of everything you think you know about existence. Not just the absence of matter, no stars, no planets, no particles floating in a void, but the absence of the void itself. No space to be empty in, no time for events to unfold within, no stage upon which the cosmic drama could play out. This is where our story begins. Not in a place, because there was no place, and not at a time, because time itself had not yet begun to tick. The Big Bang Theory tells us that everything we can observe, every galaxy spiralling through the darkness, every photon of light warming your face on a sunny day, every atom in your body, and the very space between atoms, all of it emerged from a state so unlike anything in our everyday experience that we have to stretch language to its breaking point just to begin describing it. Scientists call it a singularity, a point where the normal rules of physics as we understand them simply cease to apply. Picture trying to understand what happened by working backward from what we see today. Look around you right now at the room you're in, at the walls and furniture, the air you're breathing, even the light by which you see. All of this matter, all of this space, has a history. If you could somehow run time in reverse, you would see the room grow smaller, the air grow denser, the temperature rise. Keep going back, and you'd see the building materials return to their sources, wood to trees, metal to ore in the ground, even the atoms themselves beginning to break apart as conditions became more and more extreme. Continue this reverse journey, and you'd witness the entire Earth shrinking, its surface growing hot, its atmosphere thickening. Go further back, and you'd see our planet merge with the debris that formed it, then watch as that debris joins the swirling disk of gas and dust that gave birth to our solar system. The sun itself would grow smaller and denser, eventually joining the vast cloud of gas from which it condensed. But we're still not at the beginning. Keep rewinding, and you'd see all the stars in our galaxy drawing closer together, the space between them shrinking, their light shifting toward the blue end of the spectrum as they approach. Other galaxies would begin rushing toward us rather than away, the vast cosmic web of structure collapsing inward. The universe would grow hotter and brighter as everything compressed together. Go back far enough, about 13.8 billion years, and you'd reach a moment when all of this matter and energy, all of this space and time, was compressed into a volume smaller than a single proton. The temperature would be so high that even the fundamental particles of matter couldn't exist as we know them. The density would be so extreme that our familiar concepts of physics would break down entirely. This is the singularity that the Big Bang Theory points toward. Not a thing or a place, but the ultimate boundary of our ability to understand or describe what came before. It's a bit like asking what's north of the North Pole. The question seems reasonable, but it reaches beyond the limits of the framework we're using to ask it. From this incomprehensible beginning, space itself began to expand, not expanding into something. There was no something for it to expand into. Rather, space was creating itself as it grew, bringing time along with it like a partner in a cosmic dance. This expansion wasn't like an explosion pushing debris outward through existing space. It was more like the surface of a balloon being inflated, with every point on the surface moving away from every other point as the balloon grows larger. In those first moments, and we're talking about time intervals so brief they make the blink of an eye seem like an eternity, the universe underwent changes that would determine its entire future character. The fundamental forces that govern everything we see today were still learning how to be different from one another. In the extreme conditions of the very early universe, the electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity may have been unified into a single, more fundamental force. As the universe expanded and cooled, these forces began to separate, like different instruments in an orchestra finding their individual voices. During the first tiny fraction of a second, a period called cosmic inflation, space may have undergone a period of exponential expansion, growing faster than the speed of light. This isn't a violation of Einstein's rule that nothing can travel faster than light through space, because space itself was doing the expanding. It's a bit like being on a moving walkway at an airport. You might be walking at your normal pace relative to the walkway, but someone watching from the side would see you moving much faster than you could walk on your own. This period of inflation, if it happened, would have solved several puzzles about why our universe looks the way it does. It explains why the cosmic background radiation, that faint afterglow of creation we can still detect today, has almost exactly the same temperature in all directions. Without inflation, different regions of the early universe would have been too far apart to exchange heat and reach the same temperature. But if everything we can observe today was once compressed into a tiny region that had time to reach thermal equilibrium before inflation stretched it out, then the uniformity makes perfect sense. As inflation ended and the universe continued to expand at a more sedate pace, it began to cool from temperatures that would make the cores of the hottest stars seem frigid by comparison. In these cooling conditions, the first fundamental particles began to form. Quarks and antiquarks condensed out of the energy like droplets of matter forming in a cosmic cloud. But the universe was still far too hot for these quarks to bind together into the protons and neutrons that make up atomic nuclei today. Picture this early universe as a kind of cosmic soup, thick with particles and antiparticles being continuously created and annihilated in the intense heat. For every particle of matter that formed, there was a corresponding particle of antimatter. When they met, they would destroy each other in a flash of pure energy. Fortunately for us, there was a tiny asymmetry in this process. For every billion antimatter particles, there were 1,000,000,001 matter particles. When the great annihilation was over, that tiny excess of matter over antimatter became everything we see in the universe today. As the expansion continued and temperatures dropped further, quarks began to bind together into protons and neutrons through the strong nuclear force. This happened when the universe was still less than a second old, but by this point it had already been through transformations that determined the fundamental character of physical reality. For the next few minutes, the universe was hot and dense enough for nuclear fusion to occur throughout its entire volume. This wasn't fusion happening inside stars. There were no stars yet, no structure at all beyond the smooth, hot plasma that filled all of space. But conditions were just right for protons and neutrons to fuse together into the nuclei of the lightest elements, heavy hydrogen, helium, and a trace amount of lithium. This period of cosmic nuclear synthesis lasted only about 20 minutes, but in that brief time, the universe forged the nuclear fuel that would power the first generation of stars billions of years later. The ratios of these light elements that we observe in the universe today match the predictions of Big Bang nucleosynthesis with remarkable precision, providing some of the strongest evidence we have for this picture of cosmic origins. But even after nucleosynthesis ended, the universe was still far too hot for electrons to bind to these newly formed nuclei. Free electrons scattered photons of light so effectively that the universe remained opaque to radiation, like a thick fog that no light could penetrate. For hundreds of thousands of years, space was filled with this glowing plasma, too hot for atoms to form, too thick for light to travel freely. Only when the universe had expanded and cooled for about 380,000 years did temperatures finally drop low enough for electrons to bind to nuclei, forming the first neutral atoms. This moment, called recombination, was like the lifting of a cosmic fog. Suddenly, light could travel freely through space for the first time. The universe became transparent, and the glow of creation, now stretched by cosmic expansion into microwave radiation, began its long journey through space and time. We can still see that ancient light today, faintly glowing in every direction we look. It's called the cosmic microwave background radiation, and it's like a baby picture of the universe, showing us how things looked when the cosmos was less than 1% of its current age. The tiny temperature variations in this radiation, differences of just a few millionths of a degree, were the seeds from which all the large-scale structure of the universe would eventually grow. What's remarkable about the Big Bang theory is not just that it describes these early moments in such detail, but that its predictions can be tested against what we observe today. The expansion of the universe, the cosmic background radiation, the abundances of light elements, all of these provide independent lines of evidence that support this picture of cosmic origins. Yet there's something beautifully humble about the theory as well. It doesn't claim to answer the ultimate question of why anything exists at all, or what might have caused the Big Bang in any conventional sense. At the moment of the singularity, our normal concepts of cause and effect, of before and after, reach their limits. The Big Bang theory describes what happened once time began, but it's honest about its inability to explain why time began in the first place. This intellectual honesty echoes something found in the creation myths we discussed earlier. The ancient storytellers didn't pretend to know everything about ultimate origins either. They began their tales with mystery, with void, with chaos, with the unknowable, and described how order and structure emerged from that mystery. The Big Bang theory does something similar, beginning with a singularity that represents the boundary of human knowledge, and describing how the universe we know unfolded from that incomprehensible starting point. There's also a kind of poetry in the idea that space and time themselves have a history. We're used to thinking of space as the empty stage on which events occur, and time as the backdrop against which change happens. But the Big Bang suggests something more dynamic and strange, that space and time are part of the performance itself, characters in the cosmic story rather than just the theatre in which it unfolds. Georges Lemaitre, the Belgian physicist who first proposed what would become known as the Big Bang theory, described it as the hypothesis of the primeval atom. He imagined the entire universe beginning as a kind of cosmic egg, packed with all the energy and potential that would eventually become stars and planets and life itself. It was a vision that bridged the gap between scientific observation and mythic imagination, suggesting that creation was both a moment and a process, both a beginning and an ongoing unfolding. When Fred Hoyle coined the term Big Bang during a 1949 radio broadcast, he meant it dismissively. Hoyle preferred the idea of a steady-state universe, one that maintained constant density by continuously creating new matter as it expanded. To him, the notion of a cosmic beginning seemed unnecessarily dramatic, almost religious in its implications. But the name stuck, perhaps because it captured something essential about the theory's bold claim, that the universe had a definite beginning, a moment when everything started. Today, when we speak of the Big Bang, we're describing not just an event, but an entire framework for understanding cosmic history. It's a theory that connects the largest scales we can observe, the expansion of the universe, the distribution of galaxies, the cosmic background radiation, with the smallest scales we can probe, the behavior of fundamental particles, the nature of space and time, the origin of the elements that make up our bodies. In this framework, every atom in your body carries the story of cosmic creation within it. The hydrogen in your cells was forged in the first few minutes after the Big Bang began. The heavier elements were cooked later in the cores of stars, but even those stellar furnaces were fueled by the primordial hydrogen created in the universe's infancy. The very space your atoms occupy is itself expanding, carrying you and everything around you along on a journey that began nearly 14 billion years ago and continues to this moment. As you rest there, listening to this gentle exploration of cosmic origins, you're participating in the universe's long process of coming to understand itself. The same physical laws that governed the first moments of creation are operating in your brain as you form thoughts about those moments. The same fundamental forces that separated out in the cooling cosmic plasma are holding the molecules of your body together. You are not separate from the Big Bang. You're one of its consequences, one of the ways the universe has organized itself to contemplate its own beginning. This is perhaps the most beautiful aspect of the Big Bang theory. It suggests that consciousness itself is part of the cosmic story, that the universe's long journey from simplicity to complexity has led, at least in this small corner of space and time, to minds capable of wondering about their own origins. In understanding the Big Bang, we're not just learning about something that happened long ago and far away. We're discovering the deep history of everything we are and everything we can ever hope to become. Time, as we experience it now, flows like a gentle river, seconds following minutes, minutes gathering into hours, days unfolding into weeks with the steady, predictable rhythm of a cosmic heartbeat. But in the very beginning, time itself was learning how to exist. Those first moments of the universe unfolded not in the comfortable intervals we know, but in increments so brief that all of recorded human history would seem like an eternity by comparison. Yet within these impossibly short spans, the entire character of reality was being written. To understand how extraordinary these first moments were, imagine trying to compress all of human civilization, every thought, every discovery, every life ever lived, into the time it takes light to cross the width of a single atom. That's closer to the scale we're dealing with when we speak of the universe's first instance. Each fraction of a second contained transformations, so profound that they determined whether stars would shine, whether atoms could form, whether consciousness would ever emerge to contemplate its own origins. The very first moment we can meaningfully discuss is called the Planck epoch, lasting from time 0 until about 10 to the minus 43 seconds after the beginning. To put this in perspective, there are more Planck times in a single second than there are seconds in all the time since the Big Bang began. During this epoch, the universe was so hot and dense that our familiar concepts of space and time break down entirely. The four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single primordial force that we can barely imagine. At these energies, particles that we think of as fundamental, electrons, quarks, photons, couldn't exist as distinct entities. Instead, there was something more basic, a kind of cosmic soup of pure possibility from which all the complexity of the modern universe would eventually crystallize. Quantum effects dominated everything, and the very geometry of space itself fluctuated wildly on the smallest scales. It's humbling to realize that this first, briefest epoch represents the absolute limit of our current understanding. Beyond this boundary, our theories simply stop working, like maps that end at the edge of an uncharted sea with the ancient warning, "Here be dragons." We don't know what physical laws governed this period, or even whether our concepts of physical laws make sense in such extreme conditions. As the universe expanded and cooled past the Planck threshold, it entered what cosmologists call the Grand Unification Epoch, lasting until about 10 to the power of negative 36 seconds after the beginning. During this period, gravity began to separate from the other forces, becoming the distinct gentle giant we know today. Gentle because it's actually the weakest of the four forces, yet giant because it operates across infinite distances and never cancels out like the others can. The separation of gravity from the unified field was like the first note played in a cosmic symphony. Suddenly, space and time could begin to have the stable geometry we're familiar with, even though conditions were still unimaginably extreme. The temperature during this epoch was about 10 to the 32nd power degrees, so hot that if you somehow transported a single cubic centimetre of this primordial plasma to our solar system, it would outshine our sun by a factor of billions. But perhaps the most remarkable event in cosmic history happened next, during what physicists call the inflationary epoch. Between about 10 to the negative 36 and 10 to the negative 32 seconds after the Big Bang, the universe underwent a period of exponential expansion that stretched space faster than light could travel across it. In a time interval shorter than it takes light to cross a proton, the universe grew by a factor that would make a grain of sand larger than a basketball. This sounds impossible at first. Didn't Einstein prove that nothing can travel faster than light? But inflation doesn't involve anything moving through space faster than light. Instead, space itself expands, carrying everything with it like leaves on a flowing river. It's a bit like being on opposite ends of a moving sidewalk that's accelerating. Even if you stand perfectly still relative to the sidewalk, someone watching from the side would see you moving away from each other faster and faster. Cosmic inflation solved several puzzles that had troubled cosmologists. Without it, we couldn't explain why the universe looks so uniform in all directions, or why space appears to be geometrically flat rather than curved. But more poetically, inflation represents the universe's first great creative act, taking quantum fluctuations smaller than subatomic particles and stretching them to scales large enough to eventually become galaxies and clusters of galaxies. Think of it this way. In the quantum realm, empty space isn't really empty. It's filled with tiny fluctuations of energy, virtual particles appearing and disappearing so quickly that we can barely detect them. During inflation, these microscopic ripples were stretched across cosmic distances, frozen in place like patterns in rapidly expanding taffy. These ancient quantum whispers became the seeds from which all the structure in the universe would eventually grow. As inflation ended, the universe entered the electroweak epoch, lasting until about 10 to the minus 12 seconds after the beginning. The name comes from the fact that during this period, the electromagnetic force and the weak nuclear force were still unified as a single electroweak force. The weak force is responsible for certain types of radioactive decay and plays a crucial role in the nuclear reactions that power stars. When it finally separated from electromagnetism, it gave the universe another tool for building complexity. The temperature was still fierce, about 10 to the 15th degrees, but dropping rapidly as expansion continued. This was when the first fundamental particles that we would recognize began to appear, though they existed in forms quite different from what we see today. Quarks and electrons swam in a sea of other exotic particles, many of which had lifetimes measured in tiny fractions of seconds before decaying into more stable forms. One of the most crucial events of this epoch was the process that created the matter-antimatter asymmetry we discussed earlier. In the perfect symmetry of the very early universe, every particle should have been balanced by a corresponding antiparticle. When they met, they should have annihilated each other completely, leaving behind a universe filled with nothing but energy. The fact that we exist at all tells us that this symmetry was somehow broken during the electroweak epoch. The exact mechanism is still debated, but somehow for every billion antimatter particles, there were 1,000,000,001 matter particles. This tiny imbalance, just one part in a billion, became everything we can observe in the universe today. Every star, every planet, every atom in your body exists because of this ancient asymmetry that emerged when the universe was less than 1/1,000,000,000th of a second old. Next came the quark epoch, lasting from about 10 to the -12 to 10 to the -6 seconds after the Big Bang. By this time, all four fundamental forces had separated into their familiar forms, though the universe was still far too hot for the complex structures we know today. Quarks, the building blocks of protons and neutrons, existed as free particles in a plasma so dense and energetic that they couldn't bind together into larger structures. Imagine a cosmic foundry where the raw materials for all future atomic nuclei existed in isolation, too hot and energetic to combine. This was a universe of pure potential, filled with the components of matter, but not yet organized into the stable forms that would make chemistry and eventually biology possible. The temperature during the quark epoch was still about 1,000,000,000,000 degrees, roughly 100,000 times hotter than the core of the Sun. At these energies, protons and neutrons couldn't exist as bound particles. Instead, quarks moved freely through space, occasionally combining briefly before being torn apart again by the intense heat. This freedom came to an end during the Hadron epoch, which lasted from about 10 to the -6 to 1 second after the Big Bang. As the universe continued to expand and cool, the temperature finally dropped to the point where quarks could bind together permanently through the strong nuclear force, forming the first protons and neutrons, collectively called hadrons. This transition, known as the quark-hadron transition, was like a phase change in the cosmic plasma. Just as water suddenly becomes ice when it cools below freezing, the free quarks suddenly organize themselves into the bound particles that would serve as building blocks for all future atomic nuclei. For the first time since the initial moments of creation, stable composite particles existed in the universe. But the cosmic story was far from over. Even with protons and neutrons now stable, the universe was still too hot for them to bind together into atomic nuclei. That would require another stage of cooling, and with it, another chapter in the universe's evolution. Following the Hadron epoch came the Lepton epoch, lasting from about 1 second to 10 seconds after the Big Bang. Leptons, particles like electrons and neutrinos, dominated the energy density of the universe during this period. The temperature had dropped to about 10 billion degrees, still far hotter than the center of any star, but cool enough that some interesting nuclear physics could begin to occur. This was when Big Bang nucleosynthesis began, the cosmic process that forged the first atomic nuclei. For about 20 minutes, the entire universe served as a giant nuclear reactor, with conditions just right for protons and neutrons to fuse together into heavier elements. The delicate balance of temperature, density, and expansion rate determined exactly which elements could form, and in what proportions. The process began with the formation of heavy hydrogen, or deuterium, a proton and neutron bound together. This sounds simple, but it required precise conditions. If the universe had been slightly hotter, deuterium nuclei would have been immediately torn apart by energetic photons. If it had been slightly cooler, the nuclear reactions wouldn't have proceeded efficiently. The window for nucleosynthesis was narrow, but the universe passed through it at exactly the right pace. From deuterium, the nuclear reactions proceeded to form helium-4, the second lightest element. Some helium-3 and lithium-7 were also produced, but in much smaller quantities. Remarkably, these nuclear reactions predicted the exact ratios of light elements we observe in the universe today, providing some of the strongest evidence for the Big Bang theory. But nuclear synthesis couldn't proceed much further. There are no stable nuclei with masses of 5 or 8 atomic units, creating a gap that the Big Bang reactions couldn't bridge. Heavier elements would have to wait billions of years to be forged in the nuclear furnaces of the first stars. The universe emerged from this epoch with about 75% hydrogen and 25% helium by mass, plus traces of deuterium and lithium, proportions that have barely changed over the subsequent 13.8 billion years. After nuclear synthesis ended, the universe entered the photon epoch, which would last for hundreds of thousands of years. During this long period, radiation dominated the energy density of the universe, and photons, particles of light, controlled its expansion and cooling. But there was a problem. Free electrons in the cosmic plasma scattered these photons so effectively that light couldn't travel more than a short distance before being absorbed and re-emitted. The universe during the photon epoch was like being inside a dense fog. Even though it glowed with the heat of creation, that glow couldn't propagate freely through space. The cosmos was opaque to its own light. A glowing plasma too thick for radiation to escape. Stars couldn't form because gravity couldn't overcome the pressure of radiation. Structure couldn't develop because photons kept matter stirred up and smooth. This cosmic fog began to thin as the universe continued to expand and cool. The temperature dropped from billions of degrees to thousands, then to mere hundreds. Finally, about 380,000 years after the Big Bang began, conditions became just right for electrons to bind to atomic nuclei, forming the first neutral atoms. This moment, called recombination, was like the lifting of a cosmic veil. Suddenly, the universe became transparent to light. Photons that had been trapped in the thick plasma for hundreds of thousands of years were finally free to travel across cosmic distances. The glow of creation, now stretched by expansion into microwave radiation, began its long journey through space and time, a journey that would eventually carry it to radio telescopes on Earth, where it would be detected as the cosmic microwave background radiation. The end of the photon epoch marked the beginning of what cosmologists call the Dark Ages, not because the universe was literally dark, but because there were no stars yet to light up the cosmos with their nuclear fire. Gravity could finally begin its patient work of pulling matter together, drawing hydrogen and helium into the dense clouds that would eventually collapse to form the first generation of stars. But that's a story for another time. As we rest here in the gentle darkness, contemplating these first moments of cosmic history, we can marvel at the delicate precision required for any of this to work. If the forces had separated differently, if the matter-antimatter asymmetry had been slightly different, if the expansion rate had been a bit faster or slower, the universe we know couldn't exist. Yet here we are, the products of that ancient sequence of phase transitions and cooling, of forces separating and particles forming, of a cosmos learning how to create complexity from simplicity. Every atom in your body passed through these epochs, was forged in these cosmic fires, and carries within it the memory of those first extraordinary moments when everything began. In our next chapter, we'll explore how astronomers discovered the evidence for this remarkable story, the clues scattered throughout the universe that allowed us to piece together this timeline of creation, written in the light of distant galaxies and the faint radiation that still whispers of cosmic beginnings. Sometimes the most profound discoveries begin with the simplest observations. A curious mind notices something slightly unusual, asks a quiet question, and sets in motion a chain of inquiry that eventually transforms our understanding of everything. This is how we learn that the universe itself is expanding, not through grand theoretical proclamations, but through the patient work of astronomers who noticed that distant galaxies appeared to be moving away from us and had the courage to follow that observation wherever it might lead. Picture yourself as an astronomer in the early 1920s, working at the Mount Wilson Observatory in the hills above Los Angeles. The city below is still small enough that its lights don't interfere much with your observations, and you have access to what was then the largest telescope in the world, a 100-inch reflector that can gather more starlight than any instrument before it. Night after night you point this magnificent machine at fuzzy patches of light scattered across the sky, objects that earlier astronomers had catalogued as nebulae, thinking them to be clouds of gas within our own galaxy. But as you peer deeper into space with better instruments, you begin to see structure within these nebulae, spiral arms, bright regions that might be clusters of stars, patterns that suggest these objects are far more complex than simple gas clouds. Some of your colleagues are beginning to suspect that these nebulae might actually be entire galaxies like our own Milky Way, island universes separated from us by distances so vast they challenge comprehension. This was the situation that faced Edwin Hubble when he began his systematic study of these mysterious objects. Hubble was methodical, patient, and blessed with access to the best observational tools of his time. But more than that, he had the intellectual courage to follow the evidence even when it led to conclusions that seemed to overturn everything astronomers thought they knew about the cosmos. The key breakthrough came when Hubble began to study the light from these distant galaxies more carefully. Light, as it turns out, carries within it a kind of fingerprint that reveals not only what distant objects are made of, but also how they're moving relative to us. When an object moves away from you, the light waves it emits get stretched out, shifting toward the red end of the spectrum. When an object moves toward you, the waves get compressed, shifting toward the blue end. This phenomenon, called the Doppler effect, is something we encounter in everyday life with sound waves, the way an ambulance siren drops in pitch as it passes by. What Hubble discovered was extraordinary and unexpected. Nearly every galaxy he observed showed this redshift, indicating that they were moving away from us. Not just a few galaxies in one direction, but galaxies in all directions, as if the entire universe was expanding away from our particular vantage point. At first glance, this might suggest that we occupy some special position at the center of cosmic expansion, but Hubble and his colleagues soon realized that the situation was far stranger and more wonderful than that. The crucial insight came when Hubble plotted the relationship between how far away these galaxies were and how fast they appeared to be receding. He discovered a remarkably simple pattern. The more distant a galaxy was, the faster it was moving away from us. This relationship, now known as Hubble's law, revealed something profound about the nature of space itself. Imagine the surface of a balloon with dots marked on it to represent galaxies. As you inflate the balloon, every dot moves away from every other dot, and the farther apart two dots are, the faster they separate. From the perspective of any single dot, all the other dots appear to be moving away, with more distant dots receding faster. This is exactly the pattern Hubble observed in the real universe, suggesting that space itself is expanding, carrying galaxies along with it like dots on an inflating balloon. This discovery overturned the centuries-old assumption that the universe was static and unchanging on the larger scales. Einstein himself had been so convinced that the universe must be static that he had modified his equations of general relativity to include what he called the cosmological constant, a kind of cosmic repulsion that could balance gravity and keep the universe stable. When he learned of Hubble's discovery, Einstein reportedly called the cosmological constant his greatest mistake. Though, as we'll see later, the story of cosmic expansion is far from over. But let's pause for a moment to appreciate the observational challenge that Hubble faced. The galaxies he was studying were incredibly faint, their light having travelled for millions or billions of years to reach Earth. To measure their distances, he had to identify individual stars within them, specifically a type of variable star called a Cepheid, whose brightness changes in a regular, predictable pattern. By comparing how bright these stars appeared to how bright they actually were, Hubble could calculate how far away their host galaxies must be. This process required extraordinary patience and skill. Each photographic plate had to be exposed for hours to gather enough light from these distant objects. The measurements had to be made with painstaking precision, often requiring multiple observations to confirm results. And all of this work was done in the era before electronic detectors, when astronomers relied on photographic emulsions to capture and record the faint light from distant galaxies. What Hubble accomplished was not just a single observation, but the construction of what astronomers call the cosmic distance ladder, a series of overlapping techniques for measuring distances to increasingly remote objects. For nearby stars, we can use parallax, the apparent shift in position that occurs as Earth orbits the Sun. For more distant stars within our galaxy, we use standard candles like Cepheid variables, whose intrinsic brightness we can determine from their pulsation periods. For galaxies beyond the range of individual star observations, we use even brighter standard candles, like certain types of supernovae. Each rung of this distance ladder extends our reach further into space, but also introduces additional uncertainties. The measurement of cosmic distances remains one of the most challenging aspects of astronomy, requiring careful calibration and cross-checking of multiple techniques. Yet from Hubble's time to the present, the basic pattern has held. Distant galaxies are receding from us, with recession velocity proportional to distance. The implications of cosmic expansion extend far beyond astronomy. If the universe is expanding now, then it must have been smaller and denser in the past. Run the expansion backward in time and you arrive at the conclusion that everything we can observe was once compressed into an incredibly small hot dense state, what we now call the Big Bang. Hubble's observations provided the first strong empirical evidence for this cosmic origin story. But the story of cosmic expansion didn't end with Hubble's initial discovery. As observational techniques improved and telescopes became more powerful, astronomers were able to extend distance measurements to increasingly remote galaxies. What they found was that the universe's expansion history is more complex than initially thought. In the 1990s, two teams of astronomers using a particularly bright type of exploding star called Type Ia supernovae as standard candles made a discovery that stunned the scientific community. By studying these cosmic lighthouses at very great distances, they found that the expansion of the universe is not slowing down under the influence of gravity, as everyone had expected, but is actually accelerating. This acceleration appears to be driven by something astronomers call dark energy, a mysterious component that makes up about 68% of the universe's total energy density. Dark energy behaves very differently from ordinary matter, or even dark matter. Instead of clumping together under gravity, it appears to fill space uniformly and to exert a kind of cosmic repulsion that drives the acceleration of expansion. The discovery of cosmic acceleration brought Einstein's cosmological constant back from the dead, though in a form he never anticipated. Instead of being a finely tuned parameter designed to keep the universe static, it now appears that there is indeed a natural constant associated with empty space itself, one that drives the universe's expansion to accelerate over time. These discoveries have profound implications for the future of the universe. If dark energy continues to dominate cosmic evolution, the expansion will accelerate indefinitely. Galaxies will move apart ever faster until even nearby galaxy clusters become isolated island universes, separated by vast, empty voids. Eventually, even individual galaxies will be torn apart as space expands faster than gravity can hold them together. But such distant futures are beyond our immediate concern. What matters for our story is that these observations, from Hubble's initial discovery of cosmic expansion to the recent detection of cosmic acceleration, provide crucial evidence for the Big Bang theory. They show us a universe that has been evolving and changing over cosmic time, a universe with a definite history and a dynamic future. The beauty of this evidence lies not just in what it tells us about cosmic origins, but in how it connects the largest scales we can observe to the smallest details of particle physics and quantum mechanics. The same expansion that carries distant galaxies away from us also stretched the tiny quantum fluctuations of the early universe into the large-scale structures we see today. The cosmic microwave background radiation we detect is redshifted by billions of years of cosmic expansion. The abundances of light elements forged in Big Bang nuclear synthesis depend critically on the expansion rate during the universe's first few minutes. Each piece of evidence reinforces the others, building a coherent picture of cosmic evolution that spans from the first fraction of a second to the present day. The expanding universe discovered by Hubble is not just one isolated observation, but a cornerstone of our modern understanding of cosmic history. As you rest there in the comfortable darkness, consider that you are participating in this cosmic expansion. The space between the atoms in your body, the distance to the nearest star, the gap between our galaxy and its neighbours, all of these are gradually growing larger as the universe continues its patient expansion. You are not separate from this cosmic story, but part of it, carried along on a journey that began nearly 14 billion years ago and continues to this moment. The redshift of distant galaxies that Hubble first measured is still happening tonight, as ancient photons complete their billion-year journeys to telescopes on Earth. Each one carries information about the state of the universe, when it began its long travel through expanding space. In studying this light, astronomers are quite literally looking back in time, seeing the universe as it was when these distant galaxies were young. This cosmic archaeology allows us to trace the history of expansion from the present day back to the earliest moments we can observe, combined with our understanding of how matter and energy behave under extreme conditions. It gives us confidence in our models of what happened even earlier, during those first extraordinary moments, when the fundamental forces separated and the first particles formed. The evidence for cosmic expansion, from Hubble's pioneering observations to today's precision measurements of cosmic acceleration, forms one pillar of support for the Big Bang theory. But it's not the only evidence. In our next chapter, we'll explore another remarkable discovery: a faint glow of radiation that fills all of space, carrying with it the imprint of the universe as it was just 380,000 years after the beginning. When the cosmic fog first lifted and light could travel freely through the cosmos for the first time. Imagine being able to see light from the moment when the universe first became transparent, when the cosmic fog of the early plasma finally lifted and photons could travel freely through space for the first time. This ancient light still surrounds us, filling every cubic centimetre of the universe with a faint glow that carries within it the imprint of creation itself. We call it the cosmic microwave background radiation, and its discovery represents one of the most beautiful accidents in the history of science, a serendipitous encounter with the afterglow of the Big Bang. The story begins not in a grand observatory or a university laboratory, but in the unlikely setting of Bell Telephone Laboratories in New Jersey, where two young radio astronomers were trying to solve what seemed like a mundane technical problem. Arno Penzias and Robert Wilson had been tasked with calibrating a sensitive, horn-shaped antenna originally built for communication with early satellites. They needed to account for every possible source of unwanted noise in their system, from the electronics to the atmosphere to the antenna itself. What they found was puzzling and persistent. No matter how carefully they cleaned their equipment, no matter which direction they pointed the antenna, no matter what time of day or season they made their observations, there was always a faint hiss of radio noise present in their data. It wasn't very loud, just a few degrees above absolute zero when measured as temperature. But it was absolutely consistent and seemed to come from everywhere at once. At first they suspected their equipment. They checked and rechecked their electronics, looking for faulty connections or components that might be generating spurious signals. They even discovered that a pair of pigeons had been nesting in the antenna, leaving behind what Penzias diplomatically described as a white dielectric substance that could potentially affect their measurements. They cleaned out the nest, removed the pigeons, and scrubbed away every trace of their occupation, but the mysterious signal remained. For months, this gentle hiss continued to puzzle them. It seemed to violate the basic principle that empty space should be cold and dark, completely absent of any radio emission. Yet here was a signal that appeared to fill all of space uniformly, glowing with the faint warmth of about 3 degrees above absolute zero. Little did they know that they were detecting the most ancient light in the universe, stretched by nearly 14 billion years of cosmic expansion from the brilliant glow of creation into the whisper-quiet radio waves they were measuring. Meanwhile, just a few dozen miles away at Princeton University, a team of theoretical cosmologists led by Robert Dicker was working on the implications of the Big Bang theory. They realized that if the universe had indeed emerged from a hot, dense initial state, there should still be traces of that primordial heat permeating all of space. The early universe, they calculated, would have been filled with intense radiation, and as the cosmos expanded and cooled, this radiation should have been stretched to longer and longer wavelengths. The Princeton team predicted that this relic radiation should still be detectable today, cooled by billions of years of cosmic expansion to just a few degrees above absolute zero and shifted from visible light into the microwave portion of the electromagnetic spectrum. They were even preparing to build their own antenna to search for this cosmic background when they learned of the mysterious signal that Penzias and Wilson were trying to eliminate from their data. The connection was made through a chance conversation, and suddenly everything fell into place. The annoying noise that had been plaguing the Bell Labs antenna wasn't a technical problem to be solved. It was the echo of creation itself, the afterglow of the Big Bang stretched by cosmic expansion into the microwave portion of the spectrum. What had started as an engineering challenge became one of the most important cosmological discoveries of the 20th century. To understand why this discovery was so significant, we need to think about what the early universe was like during its first few 100,000 years. As we explored in our cosmic timeline, the universe began incredibly hot and dense, filled with a plasma of free electrons, protons, and intense radiation. In this primordial soup, photons couldn't travel very far before being absorbed and re-emitted by free electrons. The universe was opaque to its own light, like trying to see through a thick fog. But as the universe expanded and cooled, the temperature eventually dropped to the point where electrons could bind to protons, forming the first neutral hydrogen atoms. This process, called recombination, happened when the universe was about 380,000 years old and had cooled to a temperature of roughly 3,000 degrees Kelvin. Suddenly, photons were free to travel through space without being constantly scattered by free electrons. The cosmic fog lifted, and the universe became transparent for the first time. The photons that were released at this moment of recombination began a journey through space and time that continues to this day. Originally, they glowed with the warm reddish light of an object heated to 3,000 degrees. But as the universe expanded, these photons were stretched along with space itself, their wavelengths growing longer and their energy decreasing. What began as visible and infrared radiation was gradually shifted into the microwave portion of the spectrum. Today, nearly 14 billion years later, this ancient light still fills the universe, but cooled by cosmic expansion to a temperature of just 2.7 degrees above absolute zero. It provides us with a direct view of the universe as it was when it first became transparent, like a baby picture of the cosmos taken when it was less than 1% of its current age. The uniformity of the cosmic microwave background was initially striking. No matter which direction astronomers looked, the radiation had almost exactly the same temperature and intensity. This uniformity provided strong support for the Big Bang theory, because it showed that the universe had indeed passed through a hot, dense phase when it was in thermal equilibrium. Different regions that are now separated by vast distances must have been in contact with each other during the early universe, allowing them to reach the same temperature before expansion carried them apart. But as measurement techniques improved, astronomers began to detect tiny variations in the background radiation, temperature differences of just a few millionths of a degree from one region of the sky to another. Far from being a problem for the Big Bang theory, these minute fluctuations were exactly what cosmologists had been hoping to find. They represent the seeds from which all the large-scale structure of the universe would eventually grow. These tiny temperature variations correspond to regions that were slightly denser or less dense than average when the universe first became transparent. Over hundreds of millions of years, gravity would amplify these small differences, pulling matter toward the denser regions and creating the cosmic web of galaxies, clusters, and filaments we see today. The pattern of fluctuations in the cosmic microwave background provides a kind of genetic code for the universe, encoding the information that would determine how structure would form over cosmic time. The Cosmic Background Explorer satellite, launched by NASA in 1989, produced the first detailed maps of these temperature variations. The COBE mission's discovery of the fluctuations earned its principal investigators the Nobel Prize in Physics and provided compelling evidence that our understanding of cosmic evolution was on the right track. Later missions, including the Wilkinson Microwave Anisotropy Probe (WMAP) and the European Space Agency's Planck satellite, have measured these fluctuations with extraordinary precision, allowing cosmologists to determine fundamental properties of the universe with unprecedented accuracy. These measurements have revealed that ordinary matter, the stuff that makes up stars, planets, and living beings, accounts for only about 5% of the universe's total energy content. About 27% consists of dark matter, mysterious particles that don't emit light but make their presence known through gravitational effects. The remaining 68% is dark energy, the even more mysterious component that appears to be driving the accelerating expansion of the universe. The cosmic microwave background also provides evidence for cosmic inflation, the brief period of exponential expansion that may have occurred in the universe's first moments. The observed pattern of fluctuations matches remarkably well with the predictions of inflationary models, suggesting that quantum fluctuations from the earliest moments of cosmic history were indeed stretched to cosmic scales and became the seeds of all the structure we see today. Perhaps most remarkably, the cosmic microwave background allows us to determine the geometry of the universe itself. By measuring how the size of the temperature fluctuations varies across the sky, astronomers can determine whether the universe is curved or flat in its overall geometry. The observations show that space is remarkably close to being perfectly flat, another prediction of inflationary cosmology. There's something profoundly moving about the fact that this ancient light surrounds us always. As you rest there in the comfort of your surroundings, you are bathed in radiation that has been travelling through space since long before the first stars formed, before our galaxy took shape, before our solar system was even a gleam in a cosmic dust cloud. Every cubic centimetre of the space around you contains about 400 photons from this primordial glow, cooled and stretched by cosmic expansion, but still carrying information about the universe's infancy. The discovery of the cosmic microwave background represents a beautiful convergence of theoretical prediction and observational serendipity. The fact that Penzias and Wilson stumbled upon this cosmic signal while trying to eliminate it as unwanted noise reminds us that the universe is full of surprises, and that sometimes our most important discoveries come not from carefully planned searches, but from paying attention to unexpected results. In many cultures, creation stories speak of a time when the world was covered in darkness or fog, followed by a moment when light broke through and illuminated everything. The cosmic microwave background tells a similar story, but one written in the language of physics and observation. There was indeed a time when the universe was opaque, filled with a glowing fog that no light could penetrate, and there was indeed a moment when that fog lifted, allowing light to shine forth and fill the cosmos. The photons we detect today as the cosmic microwave background were present at that cosmic dawn, witnesses to the moment when the universe first became transparent. They carry within them the imprint of conditions as they were nearly 14 billion years ago, making them our most direct connection to the ancient past. In studying this radiation, we are quite literally looking at light from the cosmic dark ages, seeing the universe as it was long before the first stars began to shine. This cosmic background radiation also provides a kind of absolute reference frame for motion through the universe. Because the radiation is so uniform, we can detect our own motion relative to it by observing how it appears, slightly hotter in the direction we're moving, and slightly cooler in the direction we're moving away from. This cosmic rest frame gives us a unique perspective on our place in the expanding universe. The cosmic microwave background has been called many poetic names: the afterglow of creation, the echo of the Big Bang, the fossil radiation from cosmic birth. All of these capture something essential about what this faint signal represents: a direct connection to the moment when our universe first became filled with light. It's a reminder that we live in a cosmos with a definite history, one that we can trace back through observational evidence to its earliest observable moments. As our measurement techniques continue to improve, the cosmic microwave background will likely yield even more secrets about cosmic origins. Future missions may detect the subtle polarization patterns imprinted by gravitational waves from the inflationary epoch, providing direct evidence for those first moments of exponential expansion. Other measurements may reveal additional clues about the nature of dark matter and dark energy, or about the ultimate fate of our expanding universe. But even with what we know today, the cosmic microwave background stands as one of the most compelling pieces of evidence for the Big Bang theory. Combined with the observations of cosmic expansion we explored in our previous chapter, it provides a consistent picture of a universe that emerged from a hot, dense initial state and has been expanding and cooling ever since. In our next chapter, we'll examine a third line of evidence that further supports this picture: the observed abundances of the lightest elements in the universe, forged in the nuclear furnace of the first few minutes after the Big Bang began. These cosmic fossils provide yet another window into the earliest moments of creation, when the entire universe served as a gigantic nuclear reactor operating under conditions that will never exist again. There's something almost magical about the realization that the atoms in your body have stories to tell, stories that stretch back billions of years to moments when the entire universe served as a cosmic foundry, forging the first elements and conditions that will never exist again. The hydrogen in every molecule of water you drink, the helium that once filled birthday balloons from your childhood, even the trace amounts of lithium in certain batteries. All of these carry within them the memory of the universe's first 20 minutes, when nuclear fusion occurred, not in the cores of stars, but everywhere at once throughout the expanding cosmos. To understand this remarkable chapter in cosmic history, we need to journey back to a time when the universe was just a few minutes old, still glowing with the heat of creation, but finally cool enough for the first atomic nuclei to form. This was the epoch of Big Bang nucleosynthesis, a brief but crucial period that would determine the chemical composition of the cosmos for billions of years to come. Picture the universe at this moment. It had already expanded and cooled dramatically from its initial state, but it was still far hotter than the center of the sun. The temperature was roughly 1 billion degrees, and the entire cosmos was filled with a seething plasma of protons, neutrons, electrons, and photons, all bathed in conditions perfect for nuclear fusion. For about 20 minutes, the entire observable universe functioned as a single gigantic nuclear reactor, operating under parameters that nuclear physicists can calculate with extraordinary precision. The process began simply enough. Individual protons, the nuclei of hydrogen atoms, began to fuse with neutrons to form deuterium, also known as heavy hydrogen. Deuterium is a delicate nucleus, easily torn apart by high-energy photons, so it could only form when the universe had cooled enough that most photons lack the energy to destroy it immediately. This was a critical threshold, and the universe passed through it at exactly the right pace to allow deuterium production to begin. Once deuterium nuclei existed in sufficient numbers, they could fuse with additional protons and neutrons to form helium-3 and tritium. These nuclei, in turn, could combine to produce helium-4, the second lightest and second most abundant element in the universe. The nuclear reactions proceeded with elegant efficiency, following pathways that nuclear physicists have mapped out in exquisite detail through both theoretical calculations and laboratory experiments. But there was a crucial limitation to this cosmic nucleosynthesis. The universe was expanding and cooling rapidly, and the window for nuclear fusion was narrow. Moreover, there are no stable nuclei with masses of 5 or 8 atomic units. Creating gaps in the nuclear landscape, that Big Bang nuclear synthesis couldn't bridge. The reactions could produce hydrogen, deuterium, helium-3, helium-4, and small amounts of lithium-7, but they couldn't proceed much further up the periodic table. This limitation meant that Big Bang nuclear synthesis ended with a universe composed of roughly 75% hydrogen and 25% helium by mass, along with tiny traces of deuterium and lithium. These proportions have remained essentially unchanged over the subsequent 13.8 billion years of cosmic evolution. The heavier elements that make up planets and living beings would have to wait for a new generation of cosmic furnaces to appear, the nuclear burning cores of the first stars. What makes Big Bang nuclear synthesis such compelling evidence for the cosmic origin story is the remarkable agreement between theoretical predictions and observational data. When nuclear physicists calculate what should have happened during those first 20 minutes, taking into account the expansion rate of the universe, the temperature and density conditions, and the known properties of nuclear reactions, they predict exactly the abundances of light elements that astronomers observe today. This agreement isn't approximate, it's precise to within a few percent across several orders of magnitude in abundance. The universe contains almost exactly the amount of helium-4 that Big Bang nuclear synthesis predicts, along with the predicted traces of deuterium and lithium-7. Stars, despite billions of years of nuclear burning, have barely altered these primordial ratios. It's as if the entire cosmos still carries the chemical fingerprint of its birth. The production of helium during Big Bang nuclear synthesis is particularly telling. Stars can produce helium through nuclear fusion in their cores, but they can't account for all the helium we observe in the universe. Even if every star that has ever existed had converted all of its hydrogen into helium, which is far more than what actually happens, there still wouldn't be enough stellar helium production to match observations. The only way to explain the observed abundance of helium is to invoke a period when the entire universe was hot and dense enough for nuclear fusion to occur everywhere at once. After nuclear synthesis ended, the universe entered what cosmologists sometimes call the Dark Ages, not because it was literally dark, but because there were no stars yet to illuminate the cosmos with their light. The universe was filled with a neutral hydrogen and helium gas, along with the mysterious dark matter that makes its presence known only through gravitational effects. For millions of years, this cosmic fog drifted through space, cooling and gradually growing less dense as expansion continued. But within this seemingly empty darkness, gravity was at work. The tiny density fluctuations that had been imprinted during the inflationary epoch, the same fluctuations we see today in the cosmic microwave background, began to grow. Regions that were slightly denser than average attracted more matter, becoming denser still. Regions that were slightly less dense became emptier, as their matter was drawn away by gravitational attraction to neighbouring overdense regions. This process of gravitational collapse was slow at first, but it accelerated as time went on. The dark matter, which doesn't interact with light or ordinary matter except through gravity, began to clump together into vast, invisible halos. Within these dark matter halos, ordinary matter, the hydrogen and helium created during Big Bang nuclear synthesis, began to collect and condense. Picture these first clouds of gas slowly growing denser and more massive over millions of years. As they contracted under their own gravity, they began to heat up, converting gravitational potential energy into thermal energy. Eventually, some of these collapsing gas clouds reached a critical threshold. Their cores became hot and dense enough for nuclear fusion to ignite, and the first stars began to shine. These primordial stars were unlike anything we see in the universe today. They were made almost entirely of hydrogen and helium, lacking the heavier elements that play crucial roles in stellar evolution and planet formation. Without heavier elements to help them radiate away heat efficiently, these first stars grew to enormous sizes, perhaps 100 or even 1,000 times more massive than our Sun. They burned brilliantly but briefly, exhausting their nuclear fuel in just a few million years. When these first-generation stars reached the end of their lives, they didn't fade away quietly. The most massive ones ended their lives in spectacular supernova explosions, events so violent that they could be seen across cosmic distances. But perhaps more importantly, these stellar deaths were also cosmic acts of creation. In their final moments, these dying stars scattered the heavy elements they had forged in their nuclear cores throughout the surrounding space. For the first time since the Big Bang, the universe was seeded with carbon, oxygen, silicon, iron, and all the other elements heavier than lithium. These elements, created in stellar furnaces and dispersed by stellar explosions, mixed with the primordial hydrogen and helium to form a new generation of gas clouds with a richer chemical composition. This cosmic recycling process, stars forming from gas clouds, fusing light elements into heavy ones, then exploding and scattering those heavy elements back into space, has continued for billions of years. Each generation of stars has added to the universe's inventory of heavy elements, gradually enriching the cosmos with the chemical complexity necessary for planets and life. Our own Sun is a relatively recent participant in this ongoing story. Born about 4.6 billion years ago from a gas cloud enriched by countless generations of previous stars, it contains roughly 2% heavy elements by mass, a small but crucial fraction that allowed rocky planets like Earth to form in its vicinity. The calcium in your bones was forged in the nuclear furnace of a star that died before our solar system was born. The iron in your blood was created in a stellar core and scattered into space by a supernova explosion billions of years ago. This connection between stellar nuclear synthesis and our own existence was beautifully captured by the astronomer Carl Sagan, who often reminded his audiences that we are made of star stuff. It's not just poetic metaphor, it's literal truth. Every atom in your body heavier than hydrogen was manufactured in a stellar core and delivered to Earth through the long, patient process of cosmic evolution. The abundance patterns we observe in stars of different ages provide a kind of archaeological record of this chemical enrichment process. The oldest stars, formed when the universe was young and metal poor, contain almost no elements heavier than helium. Slightly younger stars show traces of heavier elements, while stars like our Sun, formed more recently, contain the full complement of heavy elements necessary to build terrestrial planets. This chemical archaeology allows astronomers to trace the history of element production in the universe, confirming that Big Bang nucleosynthesis produced the light elements, while stellar nucleosynthesis has been responsible for creating everything else. The theoretical predictions for both processes match observations with remarkable precision, providing independent lines of evidence for our understanding of cosmic evolution. There's something deeply satisfying about this cosmic chemistry set. The same nuclear physics that governs fusion reactions in laboratory experiments also explains what happened during the first 20 minutes after the Big Bang and what continues to happen in stellar cores today. The elements created in those early moments provided the raw material for the first stars, which in turn created the heavier elements necessary for planets and life. This interplay between Big Bang nucleosynthesis and stellar nucleosynthesis also explains why the universe has exactly the chemical composition we observe. If the early universe had been slightly hotter or cooler, if the expansion rate had been different, if the ratio of protons to neutrons had been altered even slightly, the resulting abundance of light elements would have been very different. In turn, this would have affected how the first stars formed and evolved, potentially leading to a universe with a very different chemical inventory. The precision required for this cosmic chemistry to work out properly is remarkable. The nuclear reactions that created deuterium, helium and lithium during Big Bang nucleosynthesis depend sensitively on fundamental constants like the strength of the strong nuclear force and the mass difference between protons and neutrons. Small changes in these parameters could have led to a universe with too little helium to fuel long-lived stars, or too much helium to allow hydrogen burning to proceed efficiently. As you rest there in the quiet darkness, consider that you are surrounded by this ancient stellar heritage. The oxygen you breathe was forged in a massive star and expelled into space when that star reached the end of its life. The carbon in your cells, the nitrogen in your DNA, the phosphorus in your bones, all of these elements have stories that begin in stellar cores and continue through supernova explosions, interstellar gas clouds, and the formation of new generations of stars and planets. This cosmic perspective doesn't diminish our significance, it enhances it. We are not separate from the universe, but integral parts of its ongoing evolution. The same processes that created the chemical elements in our bodies continue to operate in stellar cores throughout the cosmos. New elements are being forged at this very moment in the hearts of distant stars, and some of those elements may eventually find their way into future planets and perhaps future forms of life. The study of element abundances and stellar nuclear synthesis provides the third major pillar of evidence for the Big Bang theory, complementing the observations of cosmic expansion and the detection of the cosmic microwave background. Together, these three lines of evidence paint a coherent picture of a universe that began in an extremely hot, dense state and has been expanding, cooling, and evolving ever since. Yet even this impressive array of evidence leaves room for alternative theories and ongoing mysteries. In our next chapter, we'll explore some of the competing ideas that have been proposed to explain cosmic origins, and examine the questions that remain unanswered even within the framework of the Big Bang theory. The story of the universe, it turns out, is far from complete, and some of its most intriguing chapters may still be waiting to be written. Science has a beautiful way of staying humble in the face of mystery, even as the Big Bang theory has accumulated compelling evidence from cosmic expansion, background radiation, and element abundances. Scientists have continued to ask uncomfortable questions, to probe the theory's limitations, and to explore alternative explanations for the cosmic story we observe around us. This intellectual restlessness isn't a weakness, it's science's greatest strength, the quality that keeps our understanding growing and evolving, rather than calcifying into dogma. The questions begin at the very foundation of the Big Bang theory itself. What came before the beginning? What could have caused the universe to spring into existence from nothing? And perhaps most puzzling of all, why does the universe seem so perfectly fine-tuned for the emergence of complexity, structure, and ultimately life? These are questions that push against the boundaries of physics and philosophy, leading us into realms where our familiar concepts of cause and effect, space and time, begin to break down. Some of the most thoughtful challenges to the Big Bang model have come from within the scientific community itself. In the 1940s and 1950s, a group of brilliant astronomers and physicists led by Fred Hoyle, Herman Bondi and Thomas Gold proposed what they called the steady-state theory. This elegant alternative suggested that the universe had no beginning at all, but instead maintained constant density by continuously creating new matter as it expanded. The steady-state model was motivated by what its proponents called the perfect cosmological principle, the idea that the universe should look essentially the same, not just from every point in space, but at every moment in time. As galaxies moved apart due to cosmic expansion, new matter would spontaneously appear in the growing voids between them, condensing into new galaxies and maintaining the cosmic status quo. The universe, in this view, was eternal, always evolving but never fundamentally changing its overall character. There was something deeply appealing about this vision. It avoided the conceptual difficulties of a cosmic beginning, eliminated the need to explain what might have triggered the Big Bang, and preserved the idea that the universe was governed by timeless, unchanging laws. The continuous creation of matter required by the theory was so gradual, only about 1 hydrogen atom per cubic meter per billion years, that it would be completely undetectable by any conceivable experiment. Fred Hoyle was particularly eloquent in defending this alternative cosmology. He argued that the idea of a cosmic beginning was unnecessarily dramatic, perhaps even tinged with religious thinking, that had no place in scientific discourse. It was Hoyle who first coined the term Big Bang during a 1949 BBC radio broadcast, though he intended it somewhat dismissively, as a way of highlighting what he saw as the implausible nature of the competing theory. The steady-state theory made specific predictions that could be tested through observation. If the universe truly maintained constant properties over time, then distant galaxies, which we see as they were long ago due to light's finite travel time, should look statistically identical to nearby galaxies. Radio sources should be distributed uniformly throughout space and time. The cosmic population of different types of objects should remain stable. But as observational astronomy became more sophisticated, these predictions began to clash with reality. Radio surveys revealed that distant radio sources were more numerous than nearby ones, suggesting that the universe had indeed evolved over cosmic time. The discovery of the cosmic microwave background radiation dealt an even more serious blow to the steady-state model, because this uniform background of ancient light was a natural consequence of Big Bang cosmology, but had no obvious explanation within the steady-state framework. By the 1970s, most cosmologists had abandoned the steady-state theory, though its legacy lives on in more modern ideas. Some contemporary models invoke continuous or cyclical creation processes, and the mathematical techniques developed for steady-state cosmology have found applications in other areas of theoretical physics. But the steady-state theory was just one of many alternatives that have been proposed over the decades. Some cosmologists have explored oscillating universe models, in which the current expansion phase is just one cycle in an eternal sequence of expansion and contraction. In these scenarios, the Big Bang wasn't the absolute beginning of everything, but rather the latest in an infinite series of cosmic rebirths. Picture a universe that expands for billions of years, slows down under the influence of gravity, comes to a halt, and then begins to contract. As it shrinks, galaxies draw closer together, temperatures rise, and eventually all matter is crushed back into the hot, dense state from which the current expansion began. Then, through some mechanism not yet understood, the collapse reverses into a new expansion phase, and the cycle begins anew. These oscillating models have an intuitive appeal because they mirror a cycle we see throughout nature: the rhythm of seasons, the phases of the moon, the birth and death of stars. Ancient Hindu cosmology spoke of cosmic cycles lasting billions of years, with universes being born, maturing, dying, and being reborn in an endless wheel of time. Some modern oscillating models echo this ancient vision, though grounded in the mathematics of general relativity rather than mythological intuition. The challenge for oscillating models has always been explaining how the universe could bounce back from total collapse without violating the laws of thermodynamics. Each cycle should produce entropy, disorder, that accumulates over time. Eventually, the universe should suffer a kind of heat death, unable to reorganize itself for another cycle. Some theorists have proposed mechanisms that could refresh the cosmos during each bounce, but these remain speculative. More recently, cosmologists have developed sophisticated alternatives based on string theory and higher dimensional physics. In ekpyrotic models, our three-dimensional universe is seen as a membrane or brain floating in a higher dimensional space. Occasionally, this membrane collides with another brain, generating the hot, dense conditions we associate with the Big Bang. The cosmic expansion we observe is the aftermath of such a collision, and future collisions could trigger new cosmic epochs. These brain collision scenarios offer elegant solutions to some puzzles in standard Big Bang cosmology. They can explain why the universe appears so flat and uniform without requiring a period of cosmic inflation. They provide a natural mechanism for generating the density fluctuations that seeded galaxy formation. And they embed our cosmic story within a larger multiverse framework, where Big Bang-like events are common occurrences rather than unique mysteries. Even more speculative are quantum cosmological models that attempt to describe how the universe might have emerged from quite literally nothing at all. In quantum mechanics, the vacuum isn't truly empty, but seethes with virtual particles appearing and disappearing according to the uncertainty principle. Some theorists have suggested that the entire universe might be a kind of quantum fluctuation, a virtual particle writ large, borrowing energy from the cosmic vacuum and expanding into the reality we observe today. Lawrence Krauss has written eloquently about a universe from nothing, describing how the total energy content of the universe might actually be zero once you account for the negative energy of gravitational fields. If true, this would mean that creating a universe wouldn't violate conservation of energy. The positive energy of matter and radiation would be exactly balanced by the negative gravitational potential energy of cosmic structure. Other quantum cosmologists have explored the idea that time itself might have a quantum origin. In these models, the question, what came before the Big Bang, becomes meaningless in the same way that asking, what's north of the North Pole, is meaningless. Time, like space, would be a property of the universe rather than a stage on which cosmic events unfold. Stephen Hawking, working with James Hartle, developed a no-boundary proposal in which the universe has finite age but no definite beginning. In their mathematical framework, the history of the universe is like the surface of a sphere, finite in extent but without edges or boundaries. Just as you can travel around the Earth without ever reaching a point where the surface ends, you could theoretically trace the history of the universe backward in time without ever reaching a moment of creation. These quantum approaches to cosmology are mathematically sophisticated, but remain highly speculative. They operate at the intersection of general relativity and quantum mechanics, two theories that have resisted all attempts at unification. Until we have a complete theory of quantum gravity, these models will remain intriguing possibilities rather than testable scientific theories. Loop quantum cosmology offers another perspective on cosmic origins, suggesting that the Big Bang might have been preceded by a big bounce from a previous contracting phase. In this framework, the extreme densities near the classical Big Bang singularity are prevented by quantum effects that create a kind of cosmic trampoline, causing contraction to reverse into expansion without ever reaching infinite density. The multiverse concept has also gained prominence in recent decades, though it takes many different forms. In chaotic inflation models, our observable universe is just one bubble in an eternally inflating multiverse, where new universes are constantly being born. Each bubble universe might have different physical laws, different particle masses, or even different numbers of spatial dimensions. String theory suggests that there might be an enormous number, perhaps 10 to the power of 500 or more, of possible vacuum states, each corresponding to a universe with different physical properties. In this landscape of possibilities, our universe would be just one among countless others, and the apparent fine-tuning of physical constants might be explained by selection effects. We observe a life-friendly universe simply because we couldn't exist in any other type. But all of these alternatives, sophisticated as they may be, face the same fundamental challenge. They make few testable predictions that distinguish them clearly from standard Big Bang cosmology. The evidence that convinced most scientists to accept the Big Bang theory, cosmic expansion, background radiation, light element abundances, fits equally well with many alternative models. Without observational tests, these remain philosophical positions rather than scientific theories. There's also a deeper question lurking beneath all these cosmological speculations, the question of why anything exists at all. Even if we could fully explain how the universe emerged from a quantum vacuum, or how it bounced from a previous collapse, or how it crystallized from collisions in higher dimensions, we would still face the mystery of why there are quantum fields to fluctuate, why there are higher dimensions to contain brains, why there are physical laws to govern cosmic evolution. The philosopher Gottfried Leibniz posed this question centuries ago. Why is there something rather than nothing? It's a question that may ultimately lie beyond the reach of scientific inquiry, in the realm where physics meets metaphysics and empirical investigation encounters the limits of human understanding. Some physicists have suggested that the question itself might be meaningless, that nothing is not a coherent concept, that existence might be the only logically consistent possibility. Others have proposed that our universe might be a mathematical structure, existing not in physical space, but in the abstract realm of mathematical truth, as eternal and inevitable as the theorem that the angles of a triangle sum to 180 degrees. But perhaps the most honest answer is that we simply don't know. The Big Bang theory has been remarkably successful at describing the evolution of the universe from its earliest observable moments to the present day, but it reaches its limits at the moment of the initial singularity. What happened before that moment, what caused that moment, or whether before even has meaning in this context, these remain open questions. This uncertainty doesn't diminish the Big Bang theory's significance. Science has always progressed by carefully mapping the boundaries of knowledge, by being clear about what we understand and honest about what remains mysterious. The Big Bang theory represents our best current understanding of cosmic history, built on solid observational foundations and tested against a wide range of predictions. As you rest there in the peaceful darkness, consider that this uncertainty at the heart of cosmology is not a failure, but an invitation. Each unanswered question, each limitation of our current theories, each alternative model that remains viable, represents a frontier waiting to be explored. Future observations, from more sensitive gravitational wave detectors, from missions to map the cosmic microwave background with unprecedented precision, from telescopes that can peer deeper into space and further back in time, may help us choose among these competing visions of cosmic origin. The story of how the universe began remains unfinished, and that's exactly as it should be. Science advances not by reaching final answers, but by asking better questions, by refining our understanding step by step, by remaining open to surprises and willing to revise our deepest assumptions when new evidence demands it. The mystery of cosmic origins continues to inspire new theories, new experiments, and new ways of thinking about the fundamental nature of reality. Even as we explore the remarkable success of the Big Bang Theory, we continue to probe its limits and search for the deeper truths that may lie beyond our current understanding of how everything began. There's something wonderfully humbling about realizing that everything we can see and touch, every star that lights the night sky, every planet orbiting every sun, every atom in your body, amounts to less than 5% of what actually exists in the universe. The remaining 95% is composed of substances so mysterious that we can only detect them through their gravitational effects, so elusive that they pass through ordinary matter as if it weren't there, so strange that they challenge our most basic assumptions about the nature of reality itself. This invisible majority of the cosmos consists of what cosmologists call dark matter and dark energy, names that reflect not their colour, but our ignorance about their fundamental nature. Dark matter comprises about 27% of the universe's total energy content, while dark energy makes up roughly 68%. Together, they dominate the cosmic inventory, shaping the evolution of the universe on the largest scales while remaining almost completely mysterious to us. The story of dark matter begins with a puzzle that first emerged in the 1930s, when an astronomer named Fritz Zwicky was studying the motion of galaxies within large clusters. Using the newly developed technique of measuring Doppler shifts in galactic light, Zwicky found that galaxies were moving much faster than they should be if the only matter holding the cluster together was what he could see through his telescope. Imagine a cosmic dance where the dancers are spinning so fast that they should fly apart, yet somehow remain bound together in their cosmic ballroom. That's what Zwicky observed in galaxy clusters. Galaxies moving at speeds that should have scattered them across the universe long ago, yet clearly held in gravitational embrace by some invisible partner. He called this missing matter dunkel Materie, dark matter, and estimated that it must outweigh visible matter by at least 10 to 1. For decades, this observation remained a curious anomaly, noted but not deeply investigated. It wasn't until the 1970s that astronomer Vera Rubin and her colleagues began to study the rotation of individual galaxies, making measurements that would transform our understanding of cosmic composition. They found that stars in the outer regions of spiral galaxies were orbiting far too quickly to be held in place by the gravity of visible matter alone. Picture our own Milky Way galaxy as a vast cosmic carousel with stars arranged in spiral arms rotating around the galactic centre. According to Newton's laws, stars farther from the centre should orbit more slowly, just as the outer planets in our solar system take longer to complete their journeys around the Sun. But Rubin's observations showed that stars throughout the galactic disk maintain roughly the same orbital speed, regardless of their distance from the centre. This flat rotation curve, as astronomers call it, suggests that galaxies are embedded within vast halos of invisible matter, matter that doesn't emit, absorb or scatter light, but makes its presence known through gravitational effects. These dark matter halos apparently extend far beyond the visible edges of galaxies, containing perhaps 10 times more mass than all the stars and gas we can observe. The evidence for dark matter has only grown stronger over the decades. Gravitational lensing, the bending of light by massive objects, predicted by Einstein's general relativity, reveals dark matter's presence in galaxy clusters. Computer simulations of cosmic structure formation show that the patterns of galaxies and galaxy clusters we observe today could never have formed from ordinary matter alone. The cosmic microwave background radiation carries imprints of dark matter's influence during the universe's infancy. Yet despite overwhelming evidence for its existence, dark matter remains profoundly mysterious. We know it interacts gravitationally with ordinary matter, but it appears to be almost completely immune to electromagnetic forces. This means it doesn't emit light, doesn't reflect light, and doesn't absorb light passing through it. Dark matter particles can apparently pass through each other and through ordinary matter with barely any interaction at all. Physicists have proposed dozens of candidates for dark matter particles, from exotic relics of the early universe to hypothetical particles predicted by extensions of the standard model of particle physics. WIMPs, weakly interacting massive particles, have been leading candidates for decades, though extensive searches using increasingly sensitive detectors have failed to find direct evidence for their existence. Other possibilities include axions, incredibly light particles that were originally proposed to solve problems in quantum chromodynamics, but could also serve as dark matter. Sterile neutrinos represent another candidate, hypothetical cousins of the known neutrinos that would interact even more weakly with ordinary matter. Some theorists have even suggested that dark matter might consist of primordial black holes formed in the early universe, though observations have largely ruled out this possibility for most mass ranges. The search for dark matter has spawned a remarkable variety of experimental approaches. Deep underground laboratories shield sensitive detectors from cosmic rays, waiting for the rare occasion when a dark matter particle might collide with an atomic nucleus. Particle accelerators attempt to create dark matter particles in high-energy collisions. Space-based telescopes search for the telltale signatures that might result when dark matter particles annihilate with each other in regions of high dark matter density. But perhaps the most puzzling component of the cosmic inventory is dark energy, the mysterious force that appears to be driving the accelerating expansion of the universe. Unlike dark matter, which at least behaves in ways that are gravitationally familiar, dark energy seems to violate our intuitions about how matter and energy should behave in the cosmos. The discovery of cosmic acceleration came as a complete surprise to astronomers in the late 1990s. Two competing teams were using observations of distant supernovae to measure the expansion history of the universe, expecting to find that the expansion was gradually slowing down under the influence of gravity. Instead, they found that the expansion has been speeding up for the past several billion years, as if some unseen force were pushing the universe apart. This cosmic acceleration requires a form of energy that behaves very differently from ordinary matter, or even dark matter. While matter becomes less dense as the universe expands, the same amount of stuff spread over ever larger volumes, dark energy appears to maintain constant density as space grows. This means that as the universe expands, the total amount of dark energy increases, providing ever more fuel for accelerating expansion. The simplest explanation for dark energy is that it represents the energy of empty space itself, what physicists call vacuum energy. Quantum field theory predicts that even empty space should be filled with virtual particles popping in and out of existence, and this quantum activity should contribute to the energy content of the vacuum. The problem is that when theorists calculate how much vacuum energy there should be, they get an answer that's larger than observed by a factor of about 10 to the power of 120, perhaps the worst prediction in the history of physics. This mismatch between theoretical expectations and observational reality represents one of the deepest puzzles in modern cosmology. Either our understanding of quantum field theory is fundamentally incomplete, or dark energy has nothing to do with vacuum fluctuations and represents something entirely different that we haven't yet imagined. Some physicists have proposed that dark energy might be a dynamical field, similar to the fields that carry fundamental forces, but with properties that evolve over cosmic time. This hypothetical field, sometimes called quintessence, after the classical fifth element, could explain why dark energy appears to have become dominant only relatively recently in cosmic history, rather than overwhelming the universe from the very beginning. Other theories suggest that dark energy might not be a thing at all, but rather a sign that our understanding of gravity breaks down on cosmic scales. Just as Newton's law of gravity required modification at very high speeds, leading to Einstein's general relativity, perhaps Einstein's theory requires modification at very large distances. These modified gravity theories attempt to explain cosmic acceleration without invoking mysterious dark energy, though they face significant challenges in matching all available observations. The cosmic inventory puzzle becomes even more perplexing when we consider cosmic inflation, the hypothetical period of exponential expansion that may have occurred in the universe's first moments. Inflation was originally proposed to explain why the universe appears so uniform and geometrically flat, but it has evolved into a framework that addresses many fundamental questions about cosmic structure and evolution. During the inflationary epoch, the universe would have expanded faster than the speed of light, growing by enormous factors in tiny fractions of a second. This rapid expansion would have stretched quantum fluctuations to macroscopic scales, creating the density variations that eventually grew into galaxies and clusters. The predictions of inflationary theory match observations of the cosmic microwave background with remarkable precision. Yet inflation raises as many questions as it answers. What drove this period of exponential expansion? What brought it to an end? Why did it happen when it did, rather than at some other time in cosmic history? The hypothetical inflaton field that supposedly powered inflation is no less mysterious than dark energy, and some theorists wonder whether we're simply multiplying mysteries rather than solving them. Different models of inflation make different predictions about the details of cosmic structure formation, and future observations may help distinguish among them. Gravitational waves produced during inflation might leave detectable imprints in the polarization patterns of the cosmic microwave background. The distribution of galaxies on the largest scales might reveal signatures of the inflationary process. But some physicists question whether inflation is necessary at all. Alternative models suggest that the universe's apparent uniformity might result from processes that occurred before the Big Bang, in a previous contracting phase, or through interactions between parallel universes. These alternatives face their own challenges, but they remind us that our understanding of cosmic origins remains incomplete. The dark sector of the universe, dark matter, dark energy, and the inflaton field represents a profound challenge to our understanding of fundamental physics. We live in a cosmos dominated by components we can barely detect, driven by forces we don't understand, shaped by processes we can only infer from their distant consequences. This situation would be frustrating if it represented the end of scientific progress, but instead it marks an exciting frontier where new discoveries await. The Large Hadron Collider continues to search for evidence of dark matter particles. The James Webb Space Telescope is peering deeper into space and further back in time than ever before, potentially revealing clues about dark energy's nature and cosmic inflation's aftermath. Underground laboratories around the world maintain constant vigil for dark matter interactions, while space-based missions map the cosmic web of dark matter through gravitational lensing. Future telescopes will measure cosmic expansion with unprecedented precision, potentially revealing whether dark energy is truly constant or evolves over cosmic time. There's something beautifully poetic about living in a universe that remains so fundamentally mysterious. Just as ancient sailors knew that vast territories lay beyond their maps marked with the notation, "Here be dragons," we know that most of the cosmos consists of unknown territories waiting to be explored. The dark components of the universe don't diminish the significance of ordinary matter, they enhance it. The stars, planets, and living beings made of ordinary matter represent the universe's most complex and interesting structures, islands of intricate organization in a cosmos dominated by invisible simplicity. We are, in a very real sense, the light in a dark universe, the part of cosmic evolution that has organized itself into patterns complex enough to contemplate the whole. As you rest there in the gentle darkness, consider that you are surrounded by this cosmic mystery. Dark matter particles are likely passing through your body at every moment, as ghostly and intangible as they are abundant. The space around you is filled with dark energy, quietly driving the expansion that carries distant galaxies ever further into the cosmic night. Yet you are not separate from these mysteries. You are part of the same cosmic story that includes dark matter halos and accelerating expansion. The atoms in your body were forged in stellar cores, assembled into complex molecules through billions of years of chemical evolution, and organized into living structures capable of wondering about their place in this strange and beautiful universe. The persistence of cosmic mysteries doesn't represent a failure of scientific understanding, but rather an invitation to continued exploration. Each unanswered question, each unexplained observation, each theoretical puzzle represents a pathway toward deeper knowledge about the fundamental nature of reality. The Big Bang Theory has been remarkably successful at describing cosmic evolution from the earliest observable moments to the present day, but it has also revealed how much we still don't know. The dark sector dominates the universe's energy budget, yet remains almost completely mysterious. Cosmic inflation explains many observed features of the universe, yet relies on hypothetical fields with unknown properties. These mysteries remind us that science is not a collection of final answers, but an ongoing conversation between theory and observation, between what we think we know and what we actually measure. The universe continues to surprise us, to challenge our assumptions, and to reveal new layers of complexity and beauty that we never suspected. As our journey through cosmic origins draws toward its close, we can marvel at how far human understanding has come, from ancient creation myths to modern cosmology, from wondering about the lights in the sky to mapping the large-scale structure of space-time itself. Yet we can also appreciate how much mystery remains, how many frontiers still beckon, how many questions still await answers from future generations of cosmic explorers. And so we find ourselves here, at the end of our gentle journey through the deepest story ever told, the story of how everything began, how complexity emerged from simplicity, how a universe that started as an infinitesimal point of pure energy evolved over nearly 14 billion years into the vast, star-filled cosmos that cradles us tonight. It's a story that connects the most abstract mathematics to the most intimate details of our existence, linking the first moments of creation to this quiet evening as you rest and contemplate your place in the cosmic tapestry. What strikes me most deeply about this journey is how it transforms our understanding of what it means to be human. We are not separate from the universe looking in from the outside. We are the universe looking at itself, matter organized in such intricate patterns that it has become capable of wonder. Every thought you've had tonight, every moment of curiosity or awe represents the cosmos coming to understand its own origins through the remarkable accident of consciousness. The atoms in your body carry within them the entire history of cosmic evolution, The hydrogen that flows through your bloodstream was forged in the first few minutes after the Big Bang began, when the entire universe served as a cosmic nuclear reactor. The carbon that forms the backbone of every molecule of life was cooked in the heart of a star that lived and died before our solar system was born. The oxygen you breathe was scattered across space by stellar winds and supernova explosions, eventually finding its way to a small rocky planet where it could become part of something as extraordinary as a living, thinking being. This cosmic ancestry doesn't diminish our significance, it enhances it beyond measure. We represent something profoundly rare and precious in the universe, matter that has organized itself into patterns complex enough to contemplate beauty, to feel love, to wonder about origins and meaning. We are, quite literally, the universe dreaming about itself. The Big Bang Theory has given us more than just a scientific account of cosmic origins. It has provided us with a new kind of creation story, one written in the language of observation and experiment, rather than myth and metaphor, yet no less profound for being grounded in evidence. Like the ancient stories our ancestors told around fires under starlit skies, it speaks to our deepest need to understand where we came from and how we fit into the larger pattern of existence. The journey we've taken together tonight, from the first impossible moment when time itself began, through the separation of forces and the formation of particles, through cosmic nuclear synthesis and the lifting of the cosmic fog, through the birth of the first stars and the gradual enrichment of space with heavy elements. This journey connects us to scales of time and space that dwarf human experience, yet somehow include us as essential participants. The mysteries that remain, dark matter and dark energy, the nature of cosmic inflation, the question of what came before the beginning, these are not failures of human understanding, but invitations to continued wonder. They remind us that the universe still holds secrets waiting to be discovered, that future generations will undoubtedly see farther than we can today, just as we see farther than our predecessors who first began to piece together this extraordinary story. As you drift towards sleep tonight, you carry with you not just the facts and figures of modern cosmology, but the profound realization that you are part of an unbroken chain of cosmic evolution that stretches from the first moments of creation to this peaceful evening. You are made of star stuff, shaped by cosmic forces, connected to the deepest processes that govern the universe itself. The same physical laws that governed those first extraordinary moments continue to operate in every cell of your body. The same creativity that built galaxies from quantum fluctuations continues to unfold in every thought you think, every dream you dream. You're not a visitor to this cosmos. You are a participant in its ongoing evolution, one of the ways the universe continues to explore its own possibilities. Rest well under the gentle watch of ancient starlight, knowing that you are both infinitely small in the cosmic scheme and infinitely precious as a conscious part of creation's grand unfolding. The universe that began in mystery nearly 14 billion years ago continues its patient evolution in your dreams, carrying forward the long, beautiful story of how something came from nothing, how complexity emerged from simplicity, and how wonder found a way to contemplate itself in the vast, expanding darkness between the stars. This is the Sleepy Astronomer, wishing you sweet dreams, fellow travellers through space and time. The cosmic story continues, and you are part of its most remarkable chapter yet.